So charge distribution, right? So till now we were discussing about the Coulomb's law and different kinds of systems, right? In all the systems, if you see, what was the nature of the charge that we took into consideration? They were all point charges. But it is not necessary that all the systems in this world is made up of only point charges, right? But one thing is clear, that many point charges put together is going to give you a big charge, right? That we call it as an extended charge. Technically, you call it as an extended charge. See, just to give you a simple understanding, in your 10th grade, right, you would have learned this chapter light, right? In front of a mirror or lens, you place objects, right? So when you talk about an object, the object is of two types. One can be a point object, or it can be an extended object. See, for example, if we stand in the front of mirror, we can call ourselves as an extended object. Suppose you place a small object which is small compared to the size of the mirror itself, we'll call it as a point object. Same logic. Okay. So having said this, when you talk about the nature or the way the charges are arranged, right, the charge distribution is basically classified into three types. So obviously, one is called linear charge distribution. So linear refers to one dimension. Then you have surface charge distribution, which refers to the two dimension, and you have the volume charge distribution, which is confined to the three dimension. I hope it is clear, right? Now, having said this, if I take a, see, for example, if I take this pen, whose thickness is small, whose thickness can be ignored, but it is considered to be a straight line. On top of this, let's say the charge is distributed. So when I say the charge is distributed, it is going to be point charges, right? When you take all those things into consideration, let me say the length of this material is L, right? And the sum of all these point charges put together is capital Q, right? If you are able to define the total charge per unit length, what am I doing? I'm calculating the total charge. I'm dividing it with L. I can call it as Q by L, but how is it we are supposed to state it? The total charge per unit length is what is called as linear charge density, right? So linear charge density is going to have the unit of Coulomb per meter. It is amount of charge per unit length. Am I clear with this? Right. Similarly, if you take surface charge distribution, means let's say you take a paper. On that paper, the charge is distributed. So where is the charge distributed now? It is occupying the area of that paper. Are you able to understand? So if you are able to define the amount of charge per unit area, you call it that as the surface charge distribution, right? Which is going to be measured in terms of Coulomb per meter square, right? Similarly, what about the volume charge distribution? Obviously, the name suggests, right? You take a three-dimensional shape inside which you stuff the charge. The amount of charge distributed per unit volume. So only thing that is common is you need not memorize the statement. Anything you write in the denominator, what is the prefix you will add to it? Per unit. That's it. So amount of charge per unit length, amount of charge per unit area, amount of charge per unit volume. Makes sense, right? So these are the three kinds of charges that are present. Sorry, these are the three kinds of charge distributions that are present. Right? This is important for us to understand. You're clear? No? Tell me. This one, huh? This one. Q is the charge. Charge can either be small q or capital Q. Sum of all the charges. Right. See, to put it simple, no, just to clear your doubt, let's say this charge is dq, this charge is dq, this charge is dq. Like this, I have multiple dqs. The sum of all these dqs put together is going to give me capital Q. It's not about an atom, no. See, if you take a material, if you take this material as a whole, it is neutral by default, unless you charge it. When you say you have charged the material itself, you're trying to tell someone that you have given excess amount of positive or negative charge. It cannot have both simultaneously. That's what I breathe. See, for example, if you take this object, rub it against some surface. Due to friction, what will happen? The charges get transferred from this material to the other. right? Either of them is supposed to have excess amount of something. It can be positive or negative depending on the nature of materials. Yeah. So mostly what we do is we take these kind of charge distributions in the derivation part. So at that time, all the charge distributions are taken in such a way that each charge is uniformly distributed. What is the meaning of uniformly distributed? Means the distance of separation between each such point charge, which is summing up to the total charge, right? The distance between each such point charge is going to be a constant. Meaning, try to understand this, okay? 1 minute. So if I take this kind of a system, 1, 2, 3, 4, 5. For example, let's say there are 5 small such point charges, and let's say the length of this is going to be 10 units, whatever it is. Now, what is going to be the value of lambda for this case in terms of number? The total charge. So, count each positive as 1 unit. So, how many such units are there? 5. So, 5 units are distributed over a length of 10 units. So, what is going to be the value of lambda? It is going to be half coulomb per meter, or whatever it is, unit per unit. Okay. Now, having said this, if I take this portion, how many charges are there? Right, 2. Means these 2 charges should get distributed over a length of 4 units so that I get the same half. That is the meaning of uniform distribution. Am I clear with this? So, here the charges are uniformly distributed throughout the length, surface or volume.